The 1929 Nobel Prize in Physics went to a French physicist, Louis Victor de Broglie, who made a remarkable proposal about the nature of matter. If Einstein, in his photoelectric effect experiment, proved that light is dualistic in nature, de Broglie proposed that a particle like an electron also would behave like a wave, and as such, it should have a wavelength and a frequency. So in today's lesson, I am focusing on that, the de Broglie wavelength. So students and friends, stick around, watch, and learn. Our question number one: what is the wavelength of an electron moving at 6.25 times 10 to the 6 meters per second given this data? Mass of the electron is equal to 9.11 to 3 significant figures raised to the negative 31 kilogram, and Planck's constant 6.626 times 10 to the negative 34 joules second. So the solution to this question is simply to apply de Broglie's equation. Right? By the way, Louis Victor's surname is pronounced de Broglie. Alright, so his de Broglie's wavelength lambda is determined simply by dividing Planck's constant by the product of its mass and its non-relativistic velocity or speed, alright, which is also the momentum of the particle. So when you substitute Planck's constant divided by the product of the mass and its given velocity or speed, and doing our math, we will get this value for the wavelength, de Broglie's wavelength of this electron, equal to 1.14 raised to the negative 10 meters, or 0.114 nanometers. All right. Now, just some word of caution. Not all photon equations, all right, are applicable to particles, okay, with rest mass, such as the one we consider here, the electron, because these particles do not travel at the speed of light c. And such photon equations like frequency equals speed of light divided by the wavelength, okay, this is exclusively used for a photon, all right? Because a photon, although it is considered a particle, but it is a massless particle which travels at the speed of light c, all right? That's why this is called the frequency of a photon. But this doesn't apply to such particles like what we are considering here, all right? The electron is moving at a speed much lower than the speed of light. Likewise, the formula for finding the photon energy, which is the product of the momentum and the speed of light, also doesn't apply to these particles. However, the formula that we use in determining the de Broglie's wavelength for this electron, all right, lambda is equal to Planck's constant divided by mv. This is actually based on the formula for the energy of a photon. E is equal to Planck's constant divided by p, or momentum. Okay, what makes a photon different from particles such as electrons is that, uh, or what makes it similar, right, to particles is that it has a momentum. All right, photons do have momenta, but they are considered massless. All right, so for more clarification on that, I suggest, all right, you watch my previous video on photoelectric effect. All right, so again, this formula for uh, determining the photon energy will also apply to such particles like an electron whose given velocity or speed is far below the speed of light. Question is, what about if the particles are accelerated to almost equal to the speed of light, or at least comparable to the speed of light? Well, in such case, when we are considering speed of velocity is comparable to the speed of light, then it's a different story because the theory of relativity will now come in, right? We have to do some adjustment in describing the speed or velocity of such particles by introducing what we call Lorentz factor, all right? Now, such concept like Lorentz factor, all right, can be viewed in another past upload, all right, that I did some uh, few months ago, right? Just check on that special theory of relativity. All right. Question number 2. What is your de Broglie's wavelength if your mass is 70.0 kilogram and you are running at a speed of 5.00 meter per second? All right. So, how do you determine a person's de Broglie's wavelength? All right. Lambda is equal to Planck's constant divided by the product of your mass and your speed. That is 6.626 raised to the negative 34 joules second divided by the product of your mass 70.0 kilogram and your speed 5.00 meter per second. Doing our math, we will get the value for your de Broglie's wavelength equal to 1.89 times 10 to the negative 32 meters, or when converted to nanometers, it is equal to 1.89 raised to the negative 23 nanometers. All right? Knowing that 1 nanometer is actually equal to negative or times 10 to the negative 9 meters. So it is such a small measure of length. All right? So having a wavelength equal to that value, 1.89 raised to the negative 23 nanometers, we say that such wavelength is far smaller than the size of a typical atom, which is just about equal to the magnitude or order of magnitude 10 to the negative 10 meters. So you see, the effects of such tiny wavelengths is so small that they are never noticed in daily life, right? So while de Broglie's hypothesis that all particles do behave like a wave in our daily life, okay, we would never notice our what we call wave characteristic. Question number 3. The de Broglie wavelength of a proton is the same as the wavelength of a photon. When we compare the kinetic energies, the kinetic energy is, letter A, the same for both. Option B, greater for the proton. Option C, greater for the photon. Option D, less for the photon. The answer is, of course, letter C, greater for the photon. We say because the energy of a photon expressed as energy equals hf, or the product of Planck's constant times speed of light divided by the wavelength lambda. This energy depends only on its frequency f, or speed of light divided by lambda. Hence, it's clear that the kinetic energy of a photon is greater than that of a proton. Alright? Of course, we are assuming that the speed of the proton, a non-relativistic speed, Vp, which means that it is way less than the speed of light, c. Question number 4. Which of these is associated with an electron microscope? Option letter A, light wave. Option letter B, sound wave. Option letter C, matter wave. Option letter D, electromagnetic or EM wave. So our answer, of course, is letter C, matter wave. The waves associated with microscopic moving particles are called matter waves. This is exactly what the de Broglie hypothesis, okay, is referring to. And one of the applications of the de Broglie hypothesis is the use of an electron microscope. An electron microscope makes use of the matter waves associated with fast-moving electrons. In an optical microscope, the wavelength of light used, which is about 400 nanometers, limits our ability to see the smallest features of the specimen. Okay? A typical electron microscope, however, uses wavelengths 1,000 times smaller, which would allow us to study very fine details. So here's a schematic diagram of a transmission electron microscope, or TEM. Alright? The electrons used in a TEM, okay, are emitted from a hot cathode and then accelerated by a potential difference typically from 40 to 400 kilovolts, and they pass what we call through a condensing lens, right, which uses magnetic fields to focus the electrons into a parallel beam before they pass through the specimen. The beam then passes through two more magnetic lenses, an objective lens. All right, this objective lens forms, all right, an intermediate image of the specimen, and then there's the other magnetic lens, a projection lens, okay, that produces the final real image of the intermediate image. All right, so this is where the final image is detected. All right, the objective lens and the projection lens play the roles of the objective and eyepiece lenses, respectively, of a compound optical microscope. This final image is projected onto a fluorescent screen for viewing or photographing. The entire apparatus is included or is enclosed in a vacuum together with the specimen. All right? So it has to be enclosed in a vacuum container. All right? Otherwise, if it is not enclosed, electrons would just scatter off the air molecules and model the image. So, our last question, supposing an accelerating voltage in an electron microscope is given 15,000 volts. Okay, the question is, what is the de Broglie wavelength of the electrons if their kinetic energy is assumed negligible before they are accelerated? For solution, we have this derived equation in finding the wavelength lambda, all right, and it is equal to Planck's constant divided by the square root, all right, the square root of twice the mass, actually twice the product of the mass of the electron and its charge multiplied by the given voltage or accelerating voltage. All right, so we have to determine first the result of getting the square root of this quantity in the denominator before doing our division, dividing the Planck's constant by whatever is the result of getting the square root of these quantities in the denominator. All right, so substituting, this is the Planck's constant, and the mass of the electron, we use the quantity for the mass of the electron that was given earlier, 9.11 raised to the negative 31 kilogram. And the charge of an electron, which is 1.602 raised to the negative 19 coulomb, then multiplied by the given accelerating voltage, 15,000 volts. All right? So when we simplify, we first get the value of the quantity in the denominator. All right? So Planck's constant divided by 6.617 raised to the negative 23. This is the result of getting the square root, all right, of twice the mass, the charge, and the accelerating voltage. And finally, if we divide Planck's constant by 6.617 raised to the negative 23, we get this value for lambda equal to 1.001 times 10 to the negative 11 meters, or in nanometers, that is 1.001 times 10 to the negative 2 nanometers in 4 significant figures. All right. So what does this mean? When compared to yellow light, whose what we call wavelength is 575 nanometers, this computed de Broglie wavelength of the electron used in this microscope, we say is 57,000 times smaller, okay, than the wavelength of the center of the visible spectrum, light spectrum, and that is yellow light. That's why we say that an electron microscope is much, much better compared to an ordinary compound optical microscope that we know of, right? Thank you very much for watching. Please follow me in my FB page and please don't forget to subscribe to my YouTube channel.